Yo, what's up? It's your boy Mr. AC, and what I got for you guys today is going over primarily, and we are on year number, so let's go ahead and get started. Let us get rolling with this next question, which is a 2002 Form B question, and it's a really good one because it's pretty tough and there's a couple assumptions you have to make. So let's go ahead and go on part A, and let's go ahead and think about what part A is asking us, because again, I think it has a really great question and it can be really confusing. So let's take a look at it. So consider the differential equation. Let y equal f of x be the particular solution to the given differential equation for this interval such that y equal 2 is a tangent to the graph of f. Now, what does the word tangent mean? That just means if I have some curve like this, that means I am tangent, right? I'll draw one like maybe right here. I'm tangent to it, right? That's, sometimes we do the equation of the line tangent. Let's continue reading it though, because there's more information that is given to us. Find the x-coordinate point of the tangency. So we need to find the x-coordinate point of this tangency and determine whether f has a local maximum, local minimum, or neither. This is really important because basically what is happening is, what this problem is telling us is we need to find out whether it's a local min or a local max. Well, that means our tangent is going to have to be up here then, right? We need to find out whether our tangent is a local min or max, maybe this right here or this right here. So now we know, okay, we can assume, according to this problem now, because of what it was asking us, we can assume that y equals -2 is a horizontal tangent. Now, because it's a horizontal tangent, that means we can assume that the derivative slope, so dy dx, should equal 0. And then we have to figure out whether it's a local min or a local maximum. So let's go ahead and get rolling and let's see what we need to do. Well, guess what? Do we have the first derivative? Well, my dear friends, we do. They gave it to us right here. So we know then that the derivative should be equal to 0 in order to be a local min or a local max. So we're going to set it equal to 0. So dy dx is 0. So 0 is equal to 3 minus x divided by y. Now we just need to solve this out. So if I go to solve this out, we're going to multiply y to both sides. So something like this here, something like that here. The good news is 0 times y is 0. These cancel. And we're going to get 0 is equal to 3 minus x. Now what we can do is I'm going to add the x to both sides. I think adding the x is a lot more better than subtracting the 3, because then we're going to have to multiply by negative. But anyways, we get x is equal to 3. Boom, so there it is. So now we've answered the first question. It says find the x-coordinate point of the point of tangency. Well, we did that. The x-coordinate point is x is equal to 3. Now we need to determine whether f has a local maximum or a local minimum. Well, what we're gonna need to do is we can approach this in two different ways, by the way. Totally up to us to decide how we want to do this. But what we have to do now is we have to do a line test, something like this right here. We know that it has a dy dx right here on this point. Dy over dx is 0. So we know this is 0. Well, we need to know, does it go from positive to negative or negative to positive? And this is, becomes a little bit more difficult than what you expect it to be, because if I go to plug in, let's say we're going to plug in like we normally would. Let's say we plug in 4 and we plug in 2, right? If I plug in 2 into my derivative function, I get 3 minus 2 is 1 up here, right? And then what is y? Well, we don't know what the y value is in this particular problem. We also don't know if we plug in 4, up here, 3 minus 4 is -1 over y. Again, do we know what the y value is? No, we don't, right? And depending on the y value, it might change the sign. So what I would prefer us to do is let's go into our second derivative, right? Because our second derivative tells us concavity. If our second derivative is positive, that means that it is concave up. If our second derivative is negative, that means we are concave down. So our second derivative is actually the key that's going to allow us to solve this problem and determine whether it has a local minimum or maximum. So let's go ahead and do that. We're going to take our second derivative. By the way, there is a way to do this right here. The reason why I'm not going to do it this way is because let's get the practice on the quotient rule, right? We haven't done the quotient rule in so long. So let's take our second derivative. So I wrote the notation how the second derivative looks like. It's the derivative of y with the little power of 2 in between them, and then dx with the power of 2. So now let's go ahead and take our second derivative. So what does our second derivative look like for this particular function? Well, it's the quotient rule, and it's very similar to the product, but with the minus symbol. So we're going to go ahead and go through it. We take the derivative of the first, which is the numerator, which is -1, right? Because 3 minus x, the 3 is gone. And then this is going to become -1, like this. Then we leave the second alone. So we're going to leave the second alone. I'm just going to put parentheses for now. Boom. Subtracted by. Now we're going to leave the first alone. So 3 minus x. And then what's the derivative of y? Well, the derivative of y is not 1, because look on the bottom, it's with respect to x. So this is implicit differentiation. So this would be times dy over dx. There is no power, so we don't have to do the chain rule. Okay, then it's divided by the second squared. In this case, it's the bottom squared. So this is going to become y squared, like this. Now we can plug all the values in. What I always love to do first is I love to figure out what is dy dx. Well, we have the equation up here. So let's go ahead and plug in our points. We know it's 3 comma -2. And let's plug it in up here and see what we get, because sometimes this is completely gone and it's, you know, a slope of 0, which it should be, because right, it should be a slope of 0. So let's actually plug it in. So we know the x value is 3, so let's plug it in. 3 minus 3 divided by, and what's my y value? Well, -2. And then this is going to become 0 divided by -2. This is wonderful, because that tells me that dy dx is 0. So I can replace that with this right here. So we know this is 0. And what's 0 times anything? 0 times anything is 0, so this whole thing is gone. So really, all we have to do now is we're going to plug in our y value. Our y value is -2, like that, divided by, well, -2 squared. And we're going to get 2 over 4. And I'm going to stop now, because I don't really necessarily care about the value, but this is beautiful. The second derivative at this exact point is positive. Because it's positive, that tells me that my function is concave up at that exact point. So now we know, well, is it a local maximum or a local minimum? Well, it's got to be a local minimum because it is concave up. And that second derivative was the key. So now when it says justify your answer, I'm going to go ahead and write. Give me one moment. Okay, so this is what I wrote for our justification. Since our second derivative is positive, it is concave up, therefore it is a local minimum, right? So you can write something to that extent. You don't even have to write second derivative is positive. You could just write this notation like this over here in the corner, right? We can write this right here if you remember how to write it correctly, and just say it is greater than 0. It is concave up, therefore it is a local minimum at x equals 3, y equals -2, and then we will have concluded this question here. Pretty tough one, but hopefully that makes sense. A lot of these problems are going to utilize the second derivative to help you out to determine whether it's a local min or a local max. Let's go ahead and go to our bread and butter, which is basically part B. Let y equal g of x be the particular solution for this equation. Okay, kind of given information that we already knew with this initial condition. Find y equals f of x. They're telling us to find y equals f of x. So if I was to write PVA, just like we normally would, we were given the derivative, and it's asking us to go back into position because it's asking to find y, the original function, and they gave us an initial condition. So now I know, hey, this is separation of variables, and I gotta separate them, and I gotta take the anti, find the initial condition, plug it in, and solve it out for this function. So let's go ahead and do that. I wrote the function out right here. Well, just like we normally would, we're basically going to multiply dx to both sides. So we're going to multiply dx to both sides right here to get rid of this. And then I need to multiply y to both sides. So I need to multiply the y to both sides to get rid of the y underneath here so that all the variables are separated and they are together. So y dy is equal to 3 minus x. I'm going to put a set of parentheses just to make sure that these are together. Boom, boom. And the dx is not attached to just one. We got to put parentheses. All right, now that they're fully separated, we can go ahead and take the antiderivative like such. Let me go ahead and turn it back to blue. So this is going to become y squared over 2 is equal to, well, we're going to take the antiderivative of each one individually. I know I put a set of parentheses, but there's no power here. Like if there was a power of 3, well, yeah, we'd have to do something different. But because there is no power, we're good to go. So the antiderivative of this is 3x minus x squared plus c. This should be divided by 2. My apologies, right? X squared over 2. We have this function right here. Once I've separated and taken the antiderivative, I'm going to go ahead now and plug in my initial condition and solve for this. So negative 4 goes into the y. So I plugged in the 6 for the x variables and I plugged in the y for the y variables, and now it's just a matter of algebraic techniques. We got to solve this out. This is going to be 16 over 2, which is 8. So I'm going to write 8 right here. 3 times 6 is 18. And then this is 36 divided by 2. 36 divided by 2, well, gosh darn it. Well, it's 18. There it is. Pretty nice. We got 18 minus 18. Yeah. 18 minus 18 is 0. So we're going to get 8 is equal to C. So now that we found our C value, let's go ahead and plug it into this one right here. So let me go ahead and take a moment to write this out. So now that I rewrote this and I put the plus 8 on the outside, well, now we need to solve for y. So first thing we always do is get rid of any multiplier or anything that is in the way of getting y by itself. So we're going to multiply the 2 across. These 2 are going to cancel right here. Let me change the color because it's not as dark as I thought it would be. And then we're going to get this. We're going to distribute the 2 across. So 2 times 3x is 6x. Distribute the 2 across here. The 2's cancel. We get x squared. And then 2 times 8 is 16. That's what it's going to look like here. And then we're down to our last step. What do we do to get rid of the power of 2? Well, we're going to take the square root of both sides. And don't forget, we get plus or minus. So now the question is, which one do we keep? Well, this is the original function and the initial condition had a y value of negative 4. What that means now is because we have this negative 4, that basically tells us that our function is living underneath the xy plane. So that tells me I'm going to keep the negative square root, and then I'm going to get 6x minus x squared plus 16. And there is my final and complete answer to part B. Now, if you notice in part C, I put a little question for part C. Again, I'm gonna let you figure this out. And if you need help, the answer key is behind this document. I just wanted to go over what the questions that I thought were going to be the toughest. But let me know if you have any questions on this one. That one's pretty tough. All right, guys. Thank you. Take care. Capiche?